of logarithms. So we have laws of logarithms. Off of our formula sheet, we have 3 laws. We're going to start with the first one. It's called the product rule. It's log b of m times n. It's this one right here. Equals log b of m plus log b of n. Now it has an equal sign, so this works both ways. We could have addition signs with the same base and put them together as multiplication, or we could have multiplication and take them apart as addition. All right? So we'll start with multiplication first. Example 1, expand. So if we have log base 6 of a squared b, the a squared and the b are what to each other? What operation is happening between them? Multiplication. So if we have multiplication between anything like that, we can expand it out with addition. So we could write this as log base 6a squared plus log base 6 of b. Okay? So if we have, even if we had 3 things multiplied, we could expand them out. Okay? Make sense? We could go the other direction as well, because this rule, we can, if we have multiplication, we expand it to plus, but if we have addition, we can expand them back. We can simplify them, make them 1 log. However, do you see that this log here is base b and base b, or this log here is base 6 and base 6? The only way you can put them together is if they actually have the same base. Okay? So example 2. Write as a single logarithm. So we're going to do the basic ones first, and then we end up using all 3 logs together in order to do this. So if I have log base b of 7 plus log base b of 8, I can put them together. Why can I put them together? They're both base b, and also you don't know this yet, but if you look at this rule, in front of each of these is a 1. So I can only use this rule if in front of all of the logs I have 1s. If I have a number in front, I have to do a different step, which comes up with another log law off the list, but they have to have +1s in front. So this log has a +1 in front, and this log has a +1 in front, and they're both base b. So that's why I can put them together. If they don't have 1s in front, or not the same base, you can't put them together. Okay? So I'm going to rewrite them as log base b. And then because there's a +1 in front of, in between them, I'm actually going to do what with the 2 numbers 7 and 8? Multiply. So my answer is actually log b 56. Okay? If you can put them together and simplify, you do. That's the product rule. Then there's the quotient rule. And we're actually going to use them together. So we're going to do them separate again, and then we'll use them all these 3 laws together. So this is the quotient rule. Quotient is an answer to a division. So when I have this, I can split this up as log base b of m minus log base b of n. Now, if you notice, the previous ones all had plus ones in front, correct? This one has a plus one in front, which it needs to have. This has a plus one in front, but the log n actually has a minus one in front. So basically, anything that's in the denominator will always get a negative one in front of the log. Anything that's in the denominator. Because we're going to put them together. We're going to use the multiplication rule and the division rule. And we're going to put them together in a second. So we'll do an example. We'll do two basic examples again in expanding and simplifying, and then we're going to put both the laws together. So expand. Log base A of 6 over 7. I want you to expand it. So anything that is in the numerator gets a plus 1 in front, and anything that's in the denominator gets a negative 1 in front. So we're going to get plus 1, technically. Do we have to write plus 1? No. I'm going to put it there anyway, just to prove a point. Plus 1 log base A of 6, and then the 7's in the denominator, so I'm going to write it as minus 1 log base A of 7. Okay? I'm going to try a harder expanding one. So, what if I do this? Log base 7 a squared b over c d squared. Looks a heck of a lot harder than it really is. What was the rules that I told you? If it's in the numerator, you add, you get a plus 1. If it's in the denominator, you subtract. This just happens to have 2 in the numerator and 2 in the denominator, correct? If it exists in the denominator, it's going to get a minus 1 in front of the log. If it exists in the numerator in the top, it's going to get a plus 1. That's it. Not a really hard question. So we're going to get log base 7 with a plus 1 in front, and then an a squared. And then I'm going to get plus 1 again, log base 7 of b. Do I actually have to show the plus 1 in front? No, I'm just proving a point. So if you just went log base 7a squared plus log base 7b, you'd be correct. And then I'm going to subtract log base 7c, and then what am I going to do with the d squared? Minus it. Subtract log base 7 of d squared, and then I've expanded it. Okay? Not super tricky, is it? The rules, though, that are important here is they have to be the same base, and they have to have 1s in front of the logs, or this formulas do not work. Okay? We're going to go over power rule in a few seconds here, and power rule will fix it so that you get 1s in front if you don't have a 1 in front. Okay? So let's try this. Example 5. Write as a single logarithm. Write as a single logarithm means I'm giving you a whole bunch of questions with more than one log, okay? And you have to make it be one log. So make sure we're copying this down. So we have log base A of 6 minus log base A of 7 minus log base A of 3. So what are our rules? We have to have plus or minus 1s in front, do we? Yes. And we need to have the same base, do we? Yes. So we can put them together. So it's going to equal log base A. 6 goes where? Numerator. 7 goes where? 3 goes where? What happens when I have more than one thing in the numerator denominator? You times them. So I'm actually going to get log base A of 6 over 21, which can actually reduce. I can take a 3 out of both. So it's going to be log base A of 2 over 7. Yeah. No, you can't actually have a negative beside the log. Log graphs, which we haven't looked at yet, but log graphs all exist on the, it's a base log, all exist in the positive x values. And not 0. You can't have a 0 beside a log, and you can't have negatives. Okay. So, last example where we have 1s in front. Example 6, simplify. So this is going to say simplify, and I want to see what you would do with it. Okay? So we're going to try this one out. Log base 3 of a squared plus log base 4 of a cubed minus log base 3 of a minus log base 4 of a to the 4. Try these out. Log base 3. If it has log base 3, we put together the ones with log base 3, which is this one and this one. This one has a plus 1 in front, so the a squared goes to the top. This one has a minus 1 in front, so the a goes to the bottom. Then plus my log base 4s. So I couldn't ask for a single logarithm because they're not all the same base. So I'm going to get log base 4. This one has a plus 1 in front, so a cubed goes in the numerator. This one has a minus 1 in front, so a to the 4 goes in the denominator. And now because they're actually the same, they're a's, you can cancel. So this a crosses off one of these a's, and I'm left with 1. It's like 1 for 1. This one is 3 and this one is 4, so I cross this one off, and I cancel this one off. Remember, what are those little slashes actually? What are the slashes? They're just ones, right? Like all of these, this is just like a little 1. This is a 1. So it became a 1. This is a 1, right? This is a 1. So actually, here I'm left with log base 3 and an a in the numerator. Do I have to put it over 1 if the 1's in the denominator? No. However, this one is log base 4. The a is in the denominator, so can I just write an a here? No, I have to write a 1 over a. We agree? So what happens? What happens if there's numbers in front? Yeah. -1. Okay, power rule. This is the third one on your formula sheet. And we need power rule if there's not 1's in front. Our power rule is log b, log base b of m to the n equals, what you can do is you can take this exponent and drop it in front. N log base b to the m. So this one works both ways as well. You can take the number in front of a log, but it has to be in front of the word log, in front of the log. You can take that number in front and you can make it be the exponent, or you can take the exponent that's on a log and drop it in front. Okay? You can do either way. When there's an equal sign in a formula, it means it works either direction, right? It could be like a double-headed arrow for all it matters, in all intents and purposes. So why is the power rule helpful to us? Well, if we have a number in front, we can just take it and raise it to the exponent. We don't have a number in front, we just have a 1, and now we can put them together again. Problem fixed, right? Okay, so we're going to do a simplifying one first, then an expanding one. So example, I have no idea. What number are we on? 7? Example 7. So we're going to simplify first. Most people are really good with this simplification. The expanding, me, not so much. But simplifying people are good. So we're going to do simplify. And so we're going to have 2 log base x of 3 plus 3 log base x of 2 minus 2 log base x of 4. Okay? Two things that happened here that errors. These are the common errors, and I promise you these are going to be the answers on your test, which are not correct, which would suck. People go, oh, I can just put them together. They have common base and start putting them together right now, and they do some crazy stuff with those front numbers. Crazy, crazy things, okay? Or two, when people take the numbers and raise them up as the exponent, they take the negative with them. Don't do that. We can have plus ones in front and we can have minus ones in front. We just can't have numbers in front that aren't ones, okay? So when we use the power rule, what we're actually going to do is we're going to take that coefficient in front and raise it up. But if it's negative, we're not going to take it up and make it a negative exponent. We're going to leave the negative be there, so we don't have to work with negative exponents, which you guys don't really like doing. If you took the negative up, it wouldn't be wrong, but you'd have to deal with negative exponents, which people don't really like dealing with, okay? So what I'm going to do first is I'm going to take these numbers and I'm going to bring them up as the exponent. Because our first rule is we need to have plus or minus ones in front. Do we? No. Secondly, we have to have common bases. Do we? Yes, they're all x's, so that's good. But we can't put them together right now because they don't have plus or minus ones in front. Okay? So we're going to get this as, and you guys will spot this. Whenever they have common bases like this, they're probably putting them together. Okay? So if you see common bases, think probably put them together. So I'm going to have log base x 3 to the 2. It comes up as the exponent. Plus log base x 2 to the 3 minus log base x 4 to the 2. So do you see how it comes up as the exponent? Now, because these are numbers, we can actually literally put a number in for it, correct? We can simplify them before we even put them together. So we have log base x. And what's beside it then? 3 squared, which is 9, correct? And then we can go log base x, 2 cubed, which is 8, minus log base x, 4 squared, which is 16. And now we can put them together, right? Could we have put them together before that? Absolutely. It just would have been, we could have, but it would have been ugly, like really ugly. So if you can get around it, then don't. So we're going to go log base x. Anything with a positive 1 in front goes to the top. So this has a plus 1 in front. So the 9 goes to the top. This has a plus 1 in front. So the 8 stays on the top. This is a minus 1 in front. So the 16 goes to the bottom. What do we do with that 9 and 8? Times them. So we're going to get log x 72 over 16. What does that reduce to? 9 over 2? You can take an 8 out of both. Okay? So we can take these big expansions and we can simplify them down to 1. Most people are really good at that. Most people forget that they can take a simplified version and expand it. Okay? So let's try that. Example 8. Expand. Expand means make bigger. Log base 3 a squared b cubed over d to the 4. Expand means make bigger. Can I simplify this in any way? It's basically as simple as it can get, correct? But I can expand it out into the same base logs, right? Whatever's in the top gets a plus 1 in front. Whatever's in the bottom gets a negative 1 in front. So I'm going to get log base 3 a squared. And it's going to have a plus 1 in front of the log, correct? Because it's in the numerator. Plus 1 log base 3 of b cubed minus 1 log base 3 of d to the 4. And this is where we would have stopped before we learned the power rule. And this isn't wrong. This is correct. They just probably are going to go one more step. What do you think they might do? Put the exponents in front. So they're going to get, and it would just join the number in front. Well, the number in front's a 1. 2 times 1 is 2, right? It's not going to change it. So you're going to get 2 log base 3a plus 3 log base 3b minus 4 log base 3d. It's the difference between expand and simplify, right? Simplify means I probably gave you something really crazy looking. You're going to make it smaller because they all have the same bases. Or expand means I gave you something looking really simple, and you're like, if you don't remember what expand means, you're going to sit there and go, I can't do anything to this. It's as simple as it gets. It is as simple as it gets. I'm not asking you to simplify. I'm asking you to expand it. Okay? Oh, I tried. I just couldn't. Okay. So your homework is and make sure you practice these, because if you don't practice them, whatever you just learned will fall out of your heads. And remember, your test is Thursday next week. Page So 9.1 and 9.2, transformations and analyzing rational functions. So the original function of a rational is the equation f of x equals 1 over x. So type it into your calculator. 1 over x. Type 1 divided by x into your calculator. So if you have the TI-83s, your calculator is going to connect them because it believes that everything needs to be continuous. Like it's like, I want all graphs continuous. However, this graph isn't continuous. It has asymptotes. So with rational graphs, so with exponential graphs, you had a horizontal asymptote. With logarithmic graphs, you have a vertical asymptote. With rationals, you get both. Woohoo! I know, excitement. So the basic rational graph is 1 over x, okay? Now you're either going to have graph in this quadrant, or you're going to have a graph in this quadrant, okay? Now, how do you know which one? Well, you can just plug in and see, right? If I plug in positive 1, I get 1 over 1, correct? So at positive 1, I'm actually at 1 over 1. I'm here, correct? So then I'm also, if I plug in negative 1, I'm going to get negative 1 and negative 1. So I'm here. So what's happening is this, if you want it to be more accurate, which this is not accurate, I'm doing 1 point and then drawing an entire graph off of 1 point. So the accuracy is very minimum right now. But what's happening is it's coming along here, and then it's running along that asymptote, right? And then it's coming along here, and it's running along that asymptote. This one is running along this asymptote, and then it's running along that one. So that's how you get that curve. So if you have the TI-83s, it's going like curve like this, and then it's somehow trying to connect them up to here and then going this way, because it wants it to be continuous. This graph is not continuous. It breaks, okay? Some people can see the asymptotes, some people cannot see the asymptotes. Either way, the only part of the graph that actually exists is this blue curve here and this blue curve here. The rest is like you draw the asymptotes, but they're dashed because they don't actually exist, right? No graph can go through them. We agree? So your basic asymptotes on this graph, you have a horizontal asymptote on the x-axis. So the x-axis equation is y equals 0. And you have a vertical asymptote on the y-axis, which is the equation of x equals 0. We agree? So what happens, keep your 1 over x in your calculator, and then in y2, put in 10 over x. Okay, so the blue one, I'm going to have 1 divided by x. And then the red one, I'm going to have 10 divided by x. What's happening? Go to your table of values. So go second graph. What's happening to all your y's? So look at this one. My y on the blue, which was the original, is -1. My y on the red is now -10. My y at 0 is 1. At 10, it's 10 now. 0.5, it's 5. 0.333, it's 3. What are we multiplying by? By 10. Because it's a vertical stretch by a factor of about the x-axis. Oh my gosh. So why is that? You guys always say the vertical stretch is the number that's in front, that a, correct? The a value is my vertical stretch. I can rewrite this. I can write it as y equals 10 bracket 1 over x. Now I'm actually comparing them, am I not? What I do to the 1 over x graph, I multiplied it by 10. So now I have a 10 in front. So what is that? A vertical stretch by a factor of 10 about the x-axis. Vertical is always about the x. Does that make sense? So here it sums it up. Oh gosh, why is this? Okay. So the graph of a rational function of the form y equals a over x represents a vertical stretch by a factor of a of the graph y equals 1 over x, because y equals a over x can be written as y equals a times 1 over x. Graphs of rational functions of the form y equals a over x have separate branches that approach the vertical asymptote at x equals 0 and the horizontal asymptote at y equals 0, right? It didn't change our asymptotes at all, did it? Our asymptotes were still at 0 and 0. It didn't move those, did it? Because what moves a vertical asymptote? A horizontal translation. So a vertical asymptote is moved by a horizontal translation. And what moves a horizontal asymptote? Vertical translation. The reflections change your domains and ranges, right? But that's not, yeah. Okay. So we're going to look at this one. Type this one into your y2. Take out the 10 over x. Remember the basic function that you're changing is the 1 over x function, correct? So we're typing it into our y2. We're leaving our y1 be the basic function because it's changing to this. 6. You need to put it in brackets. 6 divided by bracket x minus 2. So you have to have it in brackets to show that it's a fraction, correct? And you have to have the x minus 2 in brackets because it's a binomial. Minus 3. So that's the original. So my asymptote moved. Both of them actually did. Why? Because I have a horizontal translation and I have a, you know, it's all coming full circle now, guys. Like, right? Like, whoo, full circle. You see my circle I'm drawing? It's more kind of lopsided. Because you start here, and then you learn, and you learn so much, and then it comes back full circle, and you're like, transformation, it's easy. Yes. Okay. So, what are the transformations we're going to do here? We are going to have what? Remember, I can write this as y equals 6. 1 over x minus 2. Not sure why I drew that one so large. Minus 3. Right? I could put that 6 in front. Could I not? Yes. So what is it? Vertical stretch by a factor of about the okay, do I have anything else? Horizontal translation 2, right? And a vertical translation, 3 down. We agree. If I wanted to draw the new graph, I would draw the old graph 1 over x, right? To just draw it properly. But I can use mapping to draw the new one. So my original is xy. We're going to go over mapping. What was your question? Okay. So the vertical stretch and the vertical translation affect which variable, x or y? The y. So we're going to get, and we do as we say, right? So we're going to get 6 times y minus 3. What's going to happen to my x? So it's going to go x plus 2. We agree? Now remember, before I had a horizontal asymptote at y equals 0, and I had a vertical asymptote at x equals 0, right, on my basic graph. Now what's my horizontal? Y equals what? What moves a horizontal asymptote? Vertical stuff. What's the vertical stuff? 3 down. So now it's going to be at y equals. And my vertical asymptote is at x equals what? So I have a vertical asymptote that's at x equals. What moves the vertical? Positive 2. Okay? What's the problem with this one? Is it in the form, can I make it into the form 1 over x and then stuff attached to it? No. So sometimes it's not in transformation notation kind of deal. That's why I didn't ask you for the transformations. I just asked you for any asymptotes. So there are rules. We're going to move ahead and we'll come back to this. Here's my rules. So flip ahead, we're going to use rules and we're going to come back. So vertical asymptotes are x equals asymptotes, correct? We agree? So vertical asymptotes are x equals parts. We agree? Now, asymptotes are where the graph does not exist. We agree? Last year in rationals, you did non-permissible values. Last year in rationals, you did non-permissible values for the denominator because your denominator can't equal 0. We agree? So you'd say x can't equal 2. And x couldn't equal 2 because if your denominator, or if x was equal to 2, your denominator would be 0, correct? So x wouldn't equal 2. What you were actually doing is you were drawing vertical asymptotes at those values because it doesn't exist there. So the vertical asymptotes are really easy to find. They're just the non-permissible values. Okay? So you factor, if you have to, because you sometimes can, factor your denominator. Your non-permissible values, your NPVs, of the factors that do not cancel. And I'll explain why that is in a second. Are your vertical asymptotes. Because you told me last year, well, you didn't tell me because I didn't have you, but if I had you last year, you would have told me that x can't equal 2, or x can't equal 7, or x can't equal something for non-permissible values, correct? If it can't equal that, that's where an asymptote exists because that's where x is not, correct? Okay, so let's go back. We're going to do vertical asymptotes first for a few questions, and then we'll come back because horizontal are a little bit more rule-wise. Okay. So for this, we're going to find any asymptotes. Well, we're just going to find vertical asymptotes first. So what we do is we're going to go factor the top and the bottom if possible. Can we do anything to the top and the bottom? No. So we just have x minus 2. So we have x minus 2 equals 0. So x would equal 2. Why do we set it equal to 0? Because the asymptote exists whenever that denominator equals 0. Full circle. We're doing this some more. This is good. Okay. So our vertical asymptote is x equals 2. Literally that easy. Yeah. Just for the vertical asymptote. We're going to come back to horizontal and intercepts in a second. It's where your denominator can't equal 0. Because when you divide by 0, it doesn't work in your calculator. Can you go 0 divided by a number? Yes. You just can't do it the other way. Okay? We'll go to the next one, and we're going to do the vertical asymptote of this one. The vertical asymptote occurs when the denominator equals 0. Remember, you can also look at these in your calculator, and people are like, well, I just look where it doesn't exist on my calculator and I'm golden. Yes, if it's like 4 or 7 or 3, but what if it's 2/3? You might not guess it correctly. I'm just going to say, it's probably not happening. Okay? So that's why we have to be able to solve it algebraically, not just looking on our calculator. So we have x plus 4 equals 0, and wherever x plus 4 equals 0 is our asymptote. We have x equals -4. Got our vertical asymptote, and we're moving on. Example 5 for the vertical asymptote. It looks way harder, but it's really not. All we have to be able to do is do what to the bottom? Factor. So we have y equals -7. What multiplies can be -4 and adds can be -3. And I can go right to brackets because there's a 1 in front of the x squared. X minus 4, x plus 1. Do either of these factors cancel off on the numerator? Is there an x minus 4 in the numerator or an x plus 1 in the numerator? No. The catch is, if they do factor off, it's going to give you a point of discontinuity, which you don't know what that is right now. That's fine. But vertical asymptotes only exist if these don't cancel off with the numerator. Do either of these cancel off? No. So they're vertical asymptotes. So you're going to get a vertical asymptote at x minus 4 equals 0 and x plus 1 equals 0. So x equals 4 and x equals -1. Because remember, the asymptotes are where the dashed lines are, so it's actually where the graph doesn't exist. We agree? Which is where non-permissible values are. I'm going to type this one into your calculator, into my calculator, just so you can see it. See what it looks like, because it's a little bit different because you actually have 2 vertical asymptotes now, right? So it is -7 divided by bracket x squared minus 3x minus 4. So I have to put my numerator in brackets, divide by my denominator in brackets, and I press graph. And it's going to get me 2 vertical asymptotes. One at -1 and one at 4. Yeah? Yeah. Okay. Okay, let's look at example 6. Oh, goodness, it's not joining me again. Come on. Come on. Come on. Oh, my. Well, there it is. It just every so often catches up. Okay. No phones out, paying attention. So, nope. You're doing the, yeah, it's based on the denominator. So on the top, we'll factor, yes, we'll factor. So we're going to get x minus 3 and x minus 2. And on the bottom, we have x minus 3. Now, the x minus 3s are going to cancel. What's left on the bottom? A 1. There's no vertical asymptotes. The only way we state vertical asymptotes is if there's something left in the denominator after you cancel. Now, can that happen? Yeah. We could factor the denominator if there was actually 2 in the bottom, right? 1 could cancel off, and you could still be left with 1, and that's your vertical asymptote. Now I want to explain what happens when these cancel. So we still have a value of x that doesn't exist, right? X doesn't exist at 3 because that's still a non-permissible value. We agree? So we know that x equals 3 is a problem. It's an issue. We're going to write it. X equals 3 is a problem. Now people will say, well, now I canceled it off. Problem gone. Problem still was there. Problem went away, but it existed. And if at any point in time you had problem is a problem. Okay? Full circle. Okay. So do we see that? So then when you guys stated non-permissible values after you canceled in grade 11, you got the question wrong every single time? Because non-permissible values have to be stated before you cancel, because at any point in time, if it's a problem, it's always a problem. Okay? Yes. So we have x equals 3. It's our problem. We agree? It is not a vertical asymptote. So what the heck is it? Well, I'll explain. So it still doesn't exist, but on my calculator, there wouldn't be a dashed vertical line through it. So it's not a vertical asymptote. It still doesn't exist. Okay? So let's find out where it also doesn't exist on the y, because actually when they cancel off, it's a point of discontinuity. It's not a vertical asymptote. It's just an open dot in your graph. The rest of the graph exists, but there's an open dot. Now, watch. When I cancel those off, what am I left with? F of x equals x minus 2. What is x minus 2? No. What is x minus 2 if you were in grade 10 and I asked you? If you're in grade 10, you don't know any of the other information that you're giving me right now. It's just a line. It's a line. You are correct. In grade 10, you would say, hey, Lepp, that's a line. It's a line, not at -2. It is a line. There is a point at -2, which is called the y-intercept, and then there's a slope of 1/1, and you would have a line. Yeah? Yes. So when they cancel off, you have... When these cancel off, we're left with what the graph actually looks like, okay? So we're going to sketch this. You're going to follow along. So you told me at -2, there exists a line, yes, but there's also a slope of 1/1. So I'm going to sketch this graph, and then I'm going to go up 1/1. Remember, we started to y-intercept, so grade 10 is coming back. Remember, grade 10 always comes back, so does grade 11. It never leaves you. If you're like, oh, I don't want it, it's still here. Doesn't matter. You have no choice. Okay. And then I could go this way, down 1, left 1. And I have myself, this is actually what your graph is going to look like on your calculator. The graph of this little f of x on your calculator looks like this. And you're like, what? Yeah, it does. Okay? Why does it look like that? Because those factors cancel off and I'm literally just left with a line, correct? But those factors did exist, did they not? Those factors existed at some point, did they not? We agree? So we know that x equals 3 is a problem. So if we go to 3, if you go second graph, you're going to see at 3 we have a problem. We're going to have an error. So if I go bracket x squared minus 5x plus 6 bracket divided by bracket x minus 3, I have to type in the original. If you don't type in the original, you're typing in a line, and there's no problem in a line, is there? So you always have to type in it. So you're like, but Lepp, there is no problem. Remember that your calculator, you guys, often believes that everything is continuous. So if you go to your table of values, you'll actually see the problem, but on my graph, it doesn't. It looks like it keeps going, doesn't it? Looks like there's no problems. So if I go second table, look, what's beside the 3? An error, which means there's an asymptote. There's a problem. So we're going to go back. And actually, at 3 here, it's not a closed dot. You actually have a line being drawn through this. And at 3, we have a what? We have a problem. A problem meaning it doesn't exist. We're not going to draw ourselves a straight vertical line because it's not a vertical line through there, right? Vertical lines cause the graph to curve. Is this graph curving? No, so it's not a vertical asymptote. It's a point of discontinuity. So we actually have just an open dot. There's an open dot here. It doesn't exist, and the graph keeps going. That's all it is. It's just a point that's open. It's a point of discontinuity. It's a point that does not exist. It causes the graph to be not continuous, which is discontinuity. Okay? Now, if you want to find the y value, For us, we think it's 1, correct? Because it looks like it's 1. But how do you find the y? To find the y of point discontinuity, so to find the y of the point of discontinuity, we plug our problem value and in this case it's x equals 3 into the simplified line. And solve for y. So what's my simplified equation? Which one of these is a simplified equation? X minus 2. So f of x is the same as y, right? So we have y equals x minus 2. And I know x equals what? What's my problem? 3. So y equals 3 minus 2. So it equals 1. So my point of discontinuity, if they ask me for it, my P of D is at 3 and 1. And a P of D, a point of discontinuity, exists when a factor cancels. When a factor cancels, you no longer have a vertical asymptote. You just have a hole in the graph, which is the point of discontinuity. Make sense? So that's all vertical asymptotes. Vertical asymptotes are based on your non-permissible values. They're based on the values that don't exist for x, because there are places, and we know from last year from rationals, that there are places where x can't exist, because if it did exist, my denominator would be 0. That's either going to get me a vertical asymptote or a point of discontinuity. How do you know? It's a vertical asymptote if the factor doesn't cancel. The point of discontinuity if the factor does cancel. That easy. Okay? So what happens, we're going to go back to here. So this is what I wrote. Factor your denominator. Your NPVs of the factors that do not cancel are the vertical asymptotes. The factors that do cancel are what? Turn into what? Are not vertical asymptotes, they're what? Yes. There's no dash. This is fun. Putting a whole bunch of dashes. Discontinuity. And then horizontal asymptotes, the y ones, just follow rules. There's 2 rules for horizontal asymptotes. 1, numerator smaller degree than denominator. Your horizontal asymptote is y equals 0 every single time. The degree is your exponent, right? So we looked at the basic graph before. An example that we looked at was y equals 1 over x, did we not? That was the very basic one. And my asymptote, my horizontal asymptote was at y equals 0, was it not? What degree is the numerator in this case? 0. It doesn't have an x, correct? What's the degree of the denominator? 1. So the smaller on top than bottom, correct? So my horizontal asymptote is at y equals 0. Checking back on previous information, what's my vertical asymptote? X equals, what was it? It was 0, wasn't it? On that very first graph? Well, why is it x equals 0? Because I have an x in my denominator. And my vertical asymptote is based on my denominator. But this is actually based on this rule. So another example that would get me this would be y equals 1 over x plus 3. What's the degree of my numerator? 0. What's the degree of my denominator? 1. Just 1. So my horizontal asymptote would be at y equals 0. My numerator is a smaller degree than my denominator. I have an asymptote on the x-axis every time. Okay? Remember it. What would my vertical asymptote be on this one? -3. That easy. Doesn't cancel, right? Yes, it's not hard. Okay? Okay, number 2. This is also an easy one. Not hard. Number 2. Same degree. Numerator. Same degree as denominator. Take a fraction of the leading coefficients. Sounds a lot worse than it is. This is actually ridiculously easy. The wording sounds terrible. So numerator, same degree as denominator, take a fraction of the leading coefficients. The leading coefficients are the coefficients that are in front of the largest exponent, right? So an example, if they're the same degree, I could go 3x plus 1 over 2x minus 1. 3x plus 1 over 2x minus 1. What degree are both of these? 1. So same degree, correct? I take the coefficients, take a fraction of the leading coefficients. The leading coefficients are the ones that are in front of x to the 1. 3 over 2, done. Horizontal asymptote at y equals 3 over 2. Literally that easy. You forget the rules, ridiculously hard. Right? What's my horizontal or my vertical asymptote at, sorry, in this one? It's a half, because you'd have 2x minus 1 equals 0, 2x equals 1, x equals a half. Not too bad, right? Okay, so let's go back to our other questions, and now we're going to answer horizontal asymptote. You guys sound way too excited. I don't even know if I can believe your excitement. Okay. Wow, this is fantastic. Okay. So example 3, we're going back to. We said there is a vertical asymptote at x equals 2 because it didn't cancel off. What's the degree of this one? It's degree 1 and degree 1. What do we do? Yeah. Horizontal asymptote, y equals 4 over 1, which is y equals 4. Done. Ridiculously easy. So if it's in the format that's not transformation format, you just use the rules. But guys, look back here. This one was in the transformed equation, so it's not everything over everything. You can't use the rules for this one. You would just say, hey, it moved 2 to the right, so it's x equals 2. Hey, it moved 3 down, it's y minus 3. So if it's in this form, you have to use transformations. But if it's complete fraction over complete fraction, you use rules. Makes sense? Very different. Yeah. Yes, but that's where you get points of discontinuity. Because something will cancel, right? So there is a degree, that is a good question. If the degree in the numerator is bigger than the degree in the denominator, because I didn't give you one of those, a factor is going to cancel and you get a point of discontinuity. So that's going to be like that last example we'll look at. Okay, so this one, degree is what? Numerator is what? 0, and degree of the denominator is what? So numerator is, so it's going to be, no, what is it every single time? 0. Horizontal asymptote, y equals 0. Example 5. The numerator is degree, the denominator is degree, numerator is smaller than the denominator, so my horizontal asymptote's at And remember, this one it had like a one like this, was like this, and on the x-axis I had my asymptote, correct? This one, here's that degree of the numerator bigger, correct? What happened in this example for us? They canceled off and we ended up with a point of discontinuity, and we ended up with no horizontals and no verticals. So think about this. If you have no vertical asymptotes, you're not going to get a horizontal as well, because you have to be left with it. So sometimes, I'm going to show you an example. Sometimes we have something like this, and I'm going to put it in factored form. So this would still be degree 2, but say we had x plus 3, x minus 2 over x plus 3, x minus 2x minus 1, let's say. Okay? So they're the same. We agree? When they're the same degree, what happens? We take a coefficient of we take the leading coefficients and make a fraction. We agree? Still going to be the same rule, because what happens here? These cancel. So what happens? I have a P of D at x equals -3. How do I get my y? Plug it back into the simplified form. So you're going to plug it back into here. Y equals -3 minus 2 over 2 times -3 minus 1, -5 over -7. So my P of D is at -3 and 5 over 7. I just plugged it back into, you plug it back in for the x of the leftover equation, right? Now, some people try and plug it into the original, and then they get 0 over 0. Of course you're going to get 0 over 0 if you plug it into the original. This is going to turn into a 0. So you can't plug it into the original, or you're going to tell me the point of discontinuity is at something in 0 every single time. It's not. That's a hint. Like, it'd be very rare that that would happen. And now I'm left with this. I'm left with y equals x minus 2 over 2x minus 1. Am I not? Do you agree? So I have a vertical asymptote at x equals 1/2. And I have a horizontal asymptote at y equals 1/2. So I take coefficient of the beginnings. So if I still am left with a rational after I cancel, I have a vertical asymptote, a horizontal asymptote, and a point of discontinuity. Now, what does that look like on a graph? It looks like a rational graph, but there's a point that doesn't exist on it. I'll type it into my calculator later here so I can show it to you. Calculator. So I'll come back to this in a second. I just want to show you. So if I go bracket, now remember this wouldn't be factored. I just put it in factored form to begin with. You probably have to factor the numerator and denominator. So the whole top in one bracket, and then the whole bottom in a bracket. 1 second. Just wait. Let me show you so that you can see it. So this is your graph. And we said there's a point of discontinuity at, so actually at 3 here, there's a little open dot. You just can't see it. So if you went to draw this graph, you would draw the whole rational graph, and then you'd have an open dot here. Your homework is that good.